Hello viewers, let us see PID controller in this video. So as we have seen in the previous classes, P means proportional and I means integral. So proportional controller leaves the steady state errors. To overcome that, we are moving for PI controller, in which the error is getting added up with respect to the response and time. So the next advanced method is PID controller, that is proportional integral derivative controller. So this is respective to the proportional controller, and this error K integral of E of t into dt uh, relates to the integral controller, and finally the KD. D means differential gain. Okay, so D of differential of this E of t into dt. So all this in put together to form the PID controller. So the equivalent Laplace transform is given here. You can see this. So let us consider with an BLDZ example for better understanding of PID controller. Let us consider if the reference speed changes from 1000 RPM to 2500 RPM. The motor is also consider the situation that the motor initially runs at 1000 RPM. So therefore the error will be 1500 RPM. So what will the P controller will do? Immediately responds to this large speed error. So as per formula, Kp into 1500, which gives a strong control command. So the integral controller will accumulate the error over the time. That is, I is equal to K integral E of t into dt. This helps the some large error may be eliminated through the proportional controller, but still some error will be available. This will be eliminated through this integral action. So in D action, that is D controller, if the motor speed rises very fast, very rapidly, then the derivative term deducts this. So it acts like a damping mechanism, and we know what is damping mechanism. So almost it is a opposite force to the increasing parameters. So this damping D will act as a damping mechanism to control the rapid increasing parameter. Here, which is the rapid increasing parameter? That is speed. So it will provide a damping control on that and reduces the overshoot. So comparatively thinking, the P controller provides these advantages, that is simple and implementation, and the response is quicker for large errors and low computational requirement, whereas it leaves the steady state error and poor load regulation. So increasing the value of Kp beyond the value may leads to high oscillations. So considering PI controller removes the steady state error, which is the demerit of PI controller, and gives good speed regulation and suitable for mainly easy implementation and digital controllers. Okay, so most of the motor drives are using PI controllers, but still needs some improvement regarding the rapid increase in the controlling parameter. So we are moving for PID controller, in which which produces the fast response with reduced overshoot. That is due to the damping control produces reduced overshoot and zero steady state error with better transient control. If we have to tune the circuit parameters very properly, so that we can get all these advantages to be used for the motor side or any application side. So the disadvantages is there is more complicated, and the derivative term is very sensitive, so that output may be very sensitive to the input parameters. So requires careful tuning and speed feedback from the sensors encoders contains the noisy signals also. So due to the sensitivity, high sensitivity, PID controller will make the output of the circuit to be fluctuated if we not tuned properly. Okay, so for next topic we will see in the further coming videos. Thank you.